So here is an inspiring question, I would say. Are there two persons in, say, Seoul with the same number of hair strands? Exact same number of hair strands. You know, you can count the number of hair strands of yours, right? So suppose that everyone in Seoul counted his or her hair strand, and then you just compare their numbers. Do you think we can always find two people with the same number of hair strands in Seoul? How do you think? Yeah, of course, there should be at least two bald people, right? With no hair, I guess. But let's just do, without those, just to assume that they have enough, many number of hair strands like most of us. How do you think? Do we still have the same two people with the exact same number of hair strands? This question is related to the Pigeonhole principle. And the answer is yes, always. Because the population in Seoul is approximately, let's say, 20 million. This Seoul and nearby cities. And number of hair strands for one person is at most, we cannot have more than this, I think. Yeah, it's 500,000. Still many, but much less than this, right? So that means we cannot have all distinct number of hair strands, because the possibility is 1, 0, 1, 2, etc. up to this, but this number is much larger than this, so we must have at least two, even more, people with exact same number of hair strands. That's basically the idea of the pigeonhole principle. Let me state the principle. It's very simple. It's trivial to prove, right? Pigeonhole principle. If n pigeons fly into, say, n pigeonholes, n plus 1, m pigeonholes, where we have this condition. I think that's wrong in the lecture note. N is bigger than m. There are more pigeons than the pigeonholes. Then there are at least two pigeons or more in the same one pigeonhole. Just trivially true, right? Because if every pigeonhole has at most one pigeon, we cannot have more than m pigeons. Very simple, but there are many interesting applications. But even though this principle is simplicity itself, problems using pigeonhole principles can be very tricky. Sometimes it's not clear at all if we can use pigeonhole principle. And a stronger version, actually we can say there are, in this situation, there are actually at least, here we can say at least n over m ceiling pigeons. In the same pigeonhole. Of course, if n is bigger than m, this number is at least 2, so you can say it's at least 2 pigeons. But we can say more than 2 if there are more pigeons. Okay. So let me give you some example. So there are, suppose that we have 75 students. Then at least say 7 students among these 75 students were born in the same month, January or February, etc. At least. Why? Because possible months are January, February up to December, so we have 12 possible months. So these are pigeons. Let's say consider these as pigeonholes. Let's say these are pigeonholes, and the pigeons are the students, 75 students. So for each student, he or she was born in some month among these. So we can think of this as pigeons fly into pigeonholes, right? And 75 over 12 ceiling is 6.7, 7 point something is this? No, 6 point something, right? 6 point something, so floor is 7. So there are at least 7 students who were born in the same month. Okay. Oh, by the way, can we prove this? Let's prove this. We can prove this by contradiction, right? Proof. I'm going to prove this statement, this stronger version. So number of pigeons in pigeonhole, say I is less than, suppose this is not true, then this is less than, must be less than n over m, right? Okay, less than m, less than this, right? So if you sum this, sum over all I, how can I say? Maybe I think it's better to have something like, let's say m equals, n equals, let's say this is equal to k. What does that mean? That means k is greater than, k is n over m is less than or equal to k and strictly greater than k minus 1, right? This is the definition, right? If this is an integer, it's the same. This is between k minus 1 and k, it will be k. So suppose that we have this. The number of pigeons in whole I is at most what? At most k minus 1, because we assume that this is not true. Okay? Is this okay? Yeah, I think I can explain a little more clearly in the new page. Okay. Let me prove this. Proof of the pigeonhole principle. So suppose every pigeonhole has at most, this is actually quite clear, at most k minus 1 pigeons, where we have k n over m k minus 1. We will find a contradiction. Then number of pigeons is of course sum of pigeons in I from 1 to m in pigeonhole, say I. But because of this assumption, this is less than or equal to m times each of these number is at most k minus 1. So, but this, what is the number of pigeons? This is n. But you can see from here, if you divide both sides by n over m greater than or equal to, less than or equal to k minus 1, which is a contradiction here. But we say that k is less than n over m here. It's a contradiction. So that's why we must have at least the ceiling of n over m pigeons. The proof is quite simple. You can just use this proof by contradiction immediately. And like I said several times, although it's very simple principle, it's very powerful. You can solve something seemingly difficult. So, for example, the number of students and the people who were born the same month, this is a very simple problem, but we have something like this. Show that any n plus 1 subset of contains two integers a, b with GCD 1, relatively prime. So if you take more than half of these numbers, then you will always find two numbers which are relatively prime to each other. That's the problem. So how can you show this? So we can use pigeonhole principle, but the important part here, or difficult part, is to identify the pigeons and the pigeonholes. It's not clear here which object we call pigeons and which object we call pigeonholes, because they are not explicitly given. But once they are suitably identified, then problem can be solved very quickly. So let's say consider n plus 1 object. We have a subset, n plus 1 subset of this set of integers 1 up to 2n, right? And we are going to set, but the idea here is that any two consecutive integers are relatively prime to each other, right? 3 and 4, they are relatively prime. 5 and 6, or 10 and 11, any k and k plus 1, GCD, this is the observation, equals 1. So observation. So we need this observation. Any two relatively prime integers are, any two consecutive integers are relatively prime. So here we will say pigeon, we will consider these as pigeons. A1 dot 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 an plus 1, and pigeonholes are going to be this, two consecutive set of two consecutive integers. 1, 2, 3, 4, 5, 6, etc. 2n minus 1 and 2n. Okay. Then how many pigeons do we have? N plus 1. Number of pigeonholes, n. And for every integer here, it must be in one of these sets, right? So really, these pigeons fly into these pigeonholes, right? And by the pigeonhole principle, pigeonhole principle, at least two numbers are in the same set. AI, AJ are in the same set. Let's say 2k minus 1, 2k, right? Is this true? Because we have more pigeons than pigeonholes. But what does that mean? They are distinct integers. This means they are exactly 2k minus 1 and 2k. One of them is this, the other is this. That means GCD must be 1. So we just found two integers whose greatest common divisor is 1. So that is the end of the proof. Okay. Here, the difficult part is to find this setting. The pigeons are these, pigeonholes are these, etc. But once you know these are pigeons and these are pigeonholes, it's quite simple. Okay. All right. Now let's talk about this example. This is a famous example. There are 6 people. Then 3 of them know each other. 3 of them are, or 3 of them do not know each other. Or in other words, if there are 6 people, no matter how you select 6 people, you can always find 3 mutual friends or 3 mutual strangers. Always. That's the statement. This is called the Ramsey number. In general, there is a statement of the Ramsey number, but yeah, we will only consider this special case. So this is an interesting situation, right? So let's say we have P1, P2. These are the 6 people, okay? Let's draw them in like that. So it's 1, 2, 3, 4, 5. P1, P2, P3, P4, P5. 3, 4, 5, 6. And I'm going to draw like, okay, maybe I can use blue line means they are friends, they know each other, and the red means they don't know each other. Okay, you can express always like that. So, for instance, we have a situation like this. We have to complete the all possible Is this right? Oh yeah, I forgot this. Then we must be able to find a triangle, red triangle or blue triangle. Can you find it? I cannot. Can you find a blue triangle? Oh, because I didn't complete this, right? Now you can see. Do you see a blue or red triangle? Yes, this is a blue triangle. Or also this. That can be more than one. But at least we have one blue triangle or one red triangle. Always, no matter how you color the edges. So let's prove this. So let's focus on 6, this last person. We have 6 here, and then 1, 2, 3, 4, 5. Right? We have to connect this dot with these 5 dots, right? With red or blue. But in total, we have 5 edges to connect. We have 5 relations, either a friend or a stranger. And because this is some kind of pigeonhole principle, by the pigeonhole principle, we have at least 3 colors, 3 edges of the same color, either blue or red. Because think of these edges as pigeons and colors as pigeonholes. There are 2 colors and 5. There are 2 pigeonholes and 5 pigeons. So 5 over 2 floor ceiling is 3. So by the pigeonhole principle, 3 edges are red or blue, all red or all blue, right? So we can, in other words, you can find 3 friends of 6 among these, or 3 strangers to 6. By symmetry, we can assume that they are friends. Suppose that we have these 6 friends. 6 has 3 friends, A, B, C. We can assume that P6 has 3 friends. The stranger's situation is the same. Say A, B, C. Okay? Now look at the relations among these 3 people. If 2 of them are friends among these A, B, C, you can complete a blue triangle, right? For instance, AB. If AB, they are friends, then we can immediately find a triangle, a blue triangle, right? Or BC or AC. If any 2 of ABC are friends, then we have 3 friends, 3 mutual friends, including 6, right? Including 6. Otherwise, what? ABC will be a mutual stranger. So, if you cannot connect this with a blue edge, they must be they don't know each other. Same here, then you get a triangle. So in any case, we will always find 3 mutual friends or 3 mutual strangers. Is this okay? This is called the Ramsey number. There are many interesting examples of using problems using a pigeonhole principle. For instance, I will see some more examples, maybe 2 more. A1 ... AN, these are integers. Then there is a consecutive subsequences, a subsequence whose sum is divisible by n. Consecutive subsequence means you select really consecutive ones, A2, A3, A4, something like that. A6, A7, A8, etc. Or just single one is okay, A5 or A5, A6, etc. You can always find, if you have a sequence, you can always find consecutive sequence like this, and the sum of this will be divisible by n. We can always do this. Okay, how can we do this? Again, this is not clear if you can use pigeonhole principle, but we can do this. Of course, the important and difficult part is the setup. Let's consider consecutive subsequences, but all starting with A1. So A1, okay, maybe partial sum. SI, where SI is the sum of integers, the sum of the first I integers, like that. Okay? How many partial sums do we have? I is from 1 to m, right? N. There are n partial sums. If one of these is divisible by n, then we are done, right? We have already found one. If n divides Si for some I, we are done, right? Because we have already found a partial consecutive subsequence whose sum is divisible by n. So we have to consider the other case. Otherwise, now assume that n is not divisible by I for all I. So none of these is divisible by n. Then now we will consider the remainder of Si when it is divided by n. So let's say Ri is the remainder of Si divided by when divided by n. Now, what is the possible value for Si? Because we assume that Si, none of Si is divisible by n, it cannot be 0. It should be one of these numbers, 1, 2, 3, up to n minus 1. So I must be one of these, not 0. So think of these as pigeonholes, and think of these as pigeons. So for each Si, we assign the remainder. Okay? So we have n pigeons, Si's, and n minus 1 pigeonholes, possible remainders of this. And because by the pigeonhole principle, we must have Si, Sj with the same remainder, Ri, Rj. The Si, Sj, they have the same remainder when divided by n. This means we can assume that I less than j. Okay, they are different. That means Sj minus Si is divisible by n because they have the same remainder. But what is this? This is sum of the integers 1 up to a1 up to ai. This is the sum of the integers from a1 to aj. That means, this means this is the sum of the integers ai plus 1, ai plus 2 up to aj. So this is a consecutive subsequence. The sum of the integers in a consecutive subsequence, and we just show that it is divisible by n. And this is the end of the proof. Okay. All right, then let's see one more example. There are like tons of problems like this, so they look very different. So you need to practice with many problems. An inventory consists of a list of 80 items. So each item is either marked available or unavailable. And in total, the condition is there are 45 available items. And the problem is, show that there are 2 available items. There exist 2 available items. Available items exactly 9 items apart. So in other words, like for example, it's a position, say 13 and position 22. The difference is 9, right? Like that. We have like an item like this. So it's position 1, 2, 3, 4, etc. We have like 80. Some of them is available, some of them are not available. So the situation is like that. Available means we have these things, etc. And exactly 45 items are available, and then we want to. Then the problem is there is always 2 items available, where the difference here is 9, like this. Difference of the position numbers are 9. This is the question. Do you have any idea? This is not an easy problem if you don't know how to solve this. Yeah, but most problems involving pigeonhole principles are like this. It's very difficult, but once you see the solution, it's very simple. Because there are many possibilities to set up the pigeons and pigeonholes. But once you know the correct setup for the pigeons and pigeonholes, it's very simple. That's usually the nature of the problems like this. So first, let's say A1, A2, A45. These are the positions of available item. So what do we want? We want to find something like AJ minus AI equals exactly 9. We want to find 2 indices, I and J, satisfying this. That's our goal. But how? But you can say this is, by the way, we can assume that they are in increasing order, of course. This means AJ equals AI plus 9, right? This is the same. In other words, we want to find 2 indices, I and J, satisfying this relation. That's our goal. Okay? So we have 45 numbers, A1, A2, etc. The idea here, the crucial idea is create another sequence consisting of these numbers. That's the idea. Okay? So consider another sequence, B1, B45, where BI is just AI plus 9. Consider another sequence, which is like this. This is a sequence obtained by adding 9 to each element over here. Okay? Then, what is the, in A1, A45, B1, the idea is, if at least one AI is equal to one BJ, then we are done, because we have this relation. So we will look at these numbers. They are positive integers, right? Because it's positions, 1, 2, 3, up to 80. The maximum of the largest number, AI, is 80. What is the maximum possible number for B? 80 plus 9, right? Because B is obtained by adding 9 to A. So everything is at most 89. Is that right? Everything is at most 89. But how many numbers do we have? 45 times 2, 90 numbers. Here we have 90 numbers. There are 90 numbers between 0 and 89. That means we must have at least 2 numbers equal. So 2 numbers are equal. But A's are all distinct, right? Because we cannot have the same number. Same here. We cannot have same 2 equal numbers for B. They are all distinct. So the only case that two numbers are equal, this means we must have one Aij is equal to one Bj. This is the only possibility. Okay? And that's it. This means Ai equals Bj is Aj plus 9. I switched I and j, but doesn't matter. This means Ai equals Aj equals Ai minus 9. So this is exactly what we wanted. Or maybe in this form, they're the same. Ai minus Aj. We just found two indices, Ai, Aj, such that their difference is 9. So that's the end of the proof. And you know, the proof is quite simple, but coming up with this idea is the difficult part. So you have to think differently. Maybe you have to try this one, and if it doesn't work, you have to try something else until you will finally get the answer, the correct argument.